Hello students, myself Kachar Devang. Today we will discuss on design of one-way slab. First, what is slab? Slab is one kind of plate structural element which is used in roof as well as floor. There is mainly four different type of slabs. First is one-way slab, second two-way slab, third one is fourth flat slab, and fourth is grid slab. Here we have only studied one-way slab and two-way slab. The main difference between one-way slab and two-way slab is depends on the ratio of longer span to shorter span. If the ratio of longer span to shorter span is more than or equal to 2, then it is classified as a two-way slab. And if the ratio of longer span to shorter span is less than 2, then it is classified into two-way slab. One-way slab is bent in only short direction, while two-way slab is bent in short direction as well as long direction. Uh, in one-way slab, main steel is provided only in shorter direction, while in two-way slab, uh, the main steel is provided in both direction. Then design step for one-way slab. First, we have to calculate effective depth. Then we have to find the effective span. Then we have to calculate load and bending moment. Then after we have to provide main steel as well as distribution steel, and then we have to check the our design in a cracking, deflection, development length, and shear. Now let us design the simply supported slab. The data is our room dimension is 3 meter by 9 meter, inner to inner. Wall thickness is 300 mm. Live load on slab is 3 kilonewton per square meter, and the material used to preparing the slab is M20 grade concrete and Fe415 grade steel. First one is to determination effective depth. So here we have to first uh, classify our slab in one-way slab or two-way slab. So I am taking the ratio of longer span to shorter span is 9 by 3 is equal to 3, which is more than 2. So I am designing our my slab as one-way slab. So for effective depth, the it is come from IS 456 code. Okay. Here is code Indian standard 456 on page number 37 and 38. Here the criteria for deflection control, and from here the vertical deflection limit that they generally be assumed to satisfy provided that span to depth ratio are not greater than the value obtained below. First one is basic value of span to effective depth ratio for span up to 10 meter. Our span is within this limit, so I am considering simply supported beam. The value is 20. Okay. So L by D is 20 into modification factor. Here in the L, I am considering shorter span is equal to 3 meter, and for determination of modification factor, it is considered from this figure number 4, modification factor for tension reinforcement. Here we have to calculate Fs. The value of Fs is 0.85 Fy, area of concrete, area of cross section of steel provided to area of cross section of steel. Area of cross section steel required to provided. I am providing the steel how much is required. So Fs is 0.58 Fy is equal to 0.58 into 415. So the value of Fs is 240. Okay. So I am considering PT from practically it is 0.6%. So you can choose 4.4, 0.8, whatever. I am considering zero point 0.6, and by this graph, uh, uh, the value of modification factor is associated to Fs 240 is approximately 1.15. Okay, so here modification factor is 1.15. I am substituting this all value in this equation and calculating D. Effective depth is 130.43 mm. I am providing higher value as 150 mm and providing 10 mm diameter bar. So my overall depth is effective depth plus half of diameter of bar plus clear cover. Cover is 20 mm and diameter of reinforcement is 10 mm. So my overall depth is 150 plus 5 plus 20 is 175. Now effective span. Effective span criteria is given at page number 34. Okay, right here. Here is effective span criteria for a simply supported beam or slab. Okay, the effective span of member that is not built integrally with the supports shall be taken as clear span. First one is clear span plus effective depth of slab or beam. Okay, first one is clear span plus effective depth, and second one is center to center support, whichever is less. Okay, so here first one is clear span plus effective depth is our clear span is for shorter dimension 3 meter plus 150 mm is equal to 3150 mm, and center to center support is clear span plus wall thickness is 3300 mm. Hence our we have to consider smaller among these two values. So effective span is 3150 mm. So L is 3.15 mm meter. Now we have to calculate our load. First we have to calculate gate load, and then floor finish and live load per meter run. Okay, I am calculating per meter width, uh, and overall depth is 0.175 meter. Gate load is counting by cross sectional area of slab into the density of concrete. So 1 into 0.175 into 25. Floor finish I am considering 0.75 meter square kilonewton per meter square, and live load is 3 kilonewton per square meter. So total load is 8.13 kilonewton per meter. It is not a factor load, so I have to convert into factor load W. So 1.5 into total load is 12.195 kilonewton per meter. Now we have to calculate bending moment. Here our span. Here our span is simply supported beam, simply supported span. Okay, of length 3.15 meter, and factor UDL load is 12.195 kilonewton per meter. For UDL load of over entire span of simply supported span, the moment is WL square by 8. So our moment is 15.13 kilonewton into meter. Now we have to find our effective depth for flexor. Okay, we have to check if our effective depth is safe for flexor or not. So our equation of ultimate moment is 0.138 fck bd square. uh, I am putting value of mu here. So 15.30 into 10 is to 6. Notice here I am providing all the values in Newton into Newton and mm only. Okay. FCK is M20 graded concrete. FCK is 20. uh, B for 1 meter is 1000. And by substituting this value, our value of effective depth is 74.04 mm required. But my provided effective depth is 150, which is very greater than this required value. So it is safe for flexor. Now provide main steel as well as distribution steel. Main steel is calculating from percentage of steel is calculated by this formula, 50 into FCK by Fy into 1 minus under root 1 minus 4.6 mu upon FCK BD square. By putting these all values in this equation, 50 into 20 upon 415, 1 minus 1 under root 1 minus 4.6, moment is 15.13 into 10 is to 6 in Newton into mm. FCK is 20, B is 1 meter, so 1000, and D is 150 square. Uh, so PT is 0.201. Our area of steel is calculating from PT into PT of effective area. So B into effective depth. By solving this, AST is 301.75 square mm, and spacing is small AST into 1000 per AST required. Small AST is area of steel, cross section of steel of one diameter, one bar of 10 mm is pi by 4 into 10 square into 1000 upon 301.75. So spacing is 260.50 mm. We have to provide the small spacing from this value. Okay, smaller value. So I am providing 10 mm diameter bar at 260 mm center to center. Uh, Main focus here, our actual provided spacing is less than spacing how much it is come here. Okay. Now distribution steel a for FE 415 minimum PT is 0.12% and for FE 250 it is 0.15 mm. I am using 6 mm diameter bar for distribution steel. So small AST is pi by 4 into 6 square is 28.27. Spacing is 28.27 upon 210 into 1000 is approx 130 mm. So I am providing 6 mm diameter bar at 130 mm center to center. Check for cracking. Check for cracking is from IS code page number 54 or 54 maybe. Okay, here on page number 46, sorry, 46. For slabs, the horizontal distance between parallel main reinforcement bar shall not be more than 3 times of effective depth. Okay, not more than 3 times of effective depth of solid slab or 300 mm. There are two cases. First one is 3 times effective depth and second is 300 mm, whichever is small. Okay. And for second one is for distribution steel. It is for 5 times effective depth, and second one is for 50 mm, whichever is smaller. Okay. So for main steel it is 3 time effective depth is 3 into 150 is 450 mm, and second one is 300. The smaller among these two value is 300 mm, but our provided spacing for main steel is 260 mm, which is small than among these two value is 300 mm is okay. It is safe. And distribution steel is 130 mm provided, which is smaller than 5 times effective depth is 750, and also smaller than 450 mm. Okay, so it is also safe. Then check for deflection. Check for deflection is first we have to calculate allowable length to effective depth ratio is 20 into modification factor. Our provided modification factor is 1.7, and 20 into 1.7 is 34 allowable value, and actual L by D is 3150 upon 150 is 21. So actual deflection is less than allowable deflection, so it is safe. Now check for shear. Here we have to check our slab is safe in shear or not. So our first we have to calculate shear force. Shear force at support is WL by 2 for UDL loading. Put the value of W 12.195 and L is 3.15. Okay, so shear force is 19.20 kilonewton. First, nominal shear stress. Nominal shear stress is come from with number 72. Here, uh, criteria clause number 40.1, nominal shear stress. The nominal shear stress in beam from uniform depth shall be obtained from following equation: tau b is equal to Vu upon Bd. So Vu upon Bd. Shear force in sorry shear force is 19.20 kilonewton. I am converting into Newton, and B is 1 meter and depth is 150 mm. So tau B is 0.128 Newton per mm square, and considering 50% bent up bar at corner, so AST is 301.92 by 2. So area of tail is half of provided is 150.96. So our PT is 100 AST by BD. In page number 73, here is equation of PT: 100 AST by BD, 100 into AST 150.96 upon B into D is 0.1 not. Okay, so we have to calculate design shear strength. It is calculating from table number 90. uh, 4M20 grade concrete, and 4M20 grade concrete, and our PT is 0.1 not, which is small than 0.15. Okay, which is small than 0.15. So for M20 graded concrete, the value of tau C design shear strength is 0.28. So tau C for less than PT smaller value of 0.15, tau C is 0.28. The value of tau C dash, okay, design shear strength. The design shear strength of concrete in beam without shear reinforcement in table number 19. Okay, for design shear strength for concrete cell tau C into K. Okay, tau C into K. The value of K is given in below. Okay, The K value is depend on overall depth of slab. Okay, our overall depth of slab is 175. So the K value for 175 is 1.25. Okay, so K into tau c 1.25 into 0.28. So tau c dash is 0.35 Newton per square mm. So our nominal shear stress which coming on slab is small than design shear strength of slab, hence it is safe. And at final, the schematic diagram of our one-way slab. Here is one-way slab of effective depth 175 and clear span of 300 mm, so 3 meter. The main steel is provided here, the horizontal line, which is main steel of 10 mm diameter at 260 mm center to center, and distribution steel which is shown as dots, which is 6 mm diameter at 130 mm center to center, which is resting on 300 mm wall, and these two sided bent up bar, 50% bent up bar, alternate bent up bar is also provided here and here. Okay, I hope you all understand this video. Thank you.